Much, Brian. I appreciate it. And as Brian said, welcome everyone. This is Uptiv Advanced Manufacturing webinar for 3D printing versus CNC machining, which one and when. Next slide, Brian. All right, so just a little brief introduction. My name is Jesse Lee. I am the Director of Business Development for Uptiv Manufacturing. I wanted to give a little bit of a brief company overview. We'll talk through some of the technologies that we offer, and then get into the meat of the presentation. So this should just be a quick early overview. So starting here, Uptiv provides parts in prototype through production, plastic, metal, and elastomer. So we have a wide range of capabilities to address customer needs. So we come at this from an objective perspective of what do you need for your project? What are you trying to achieve so that we can recommend the correct process? So that means that we have an open-minded, objective view on what it is that we might recommend. Brief company overview. GoProto and 3 other companies were acquired by Core Industrial Partners and assembled into the platform called Uptiv. We are the second largest HP MJF service provider in the US with 14 printers. We also are one of the largest Mark Ford service providers with 15 printers at our facility in Libertyville, Illinois, just outside of Chicago. We also have machining centers in the US and overseas. So we do 2.5, 3, and 5-axis CNC machining, both in plastics and metals. So we have a huge range of capabilities with these 2 processes. We use them very often in projects, every day. So we, again, come at this objectively so that we can recommend the right process. So we have all tools in the toolbox. It's just a matter of when it makes sense to use it. So we want to go through this with you today and talk about when you might use it, how it might work for your projects. All right, so let's start looking at where does additive manufacturing make sense. Initially, additive manufacturing is the process. Let's talk about that versus 3D printing first. Additive manufacturing is using 3D printing in higher quantity to be able to make production and prototype parts in a 3D printing format. So some of the times when 3D printing or additive manufacturing makes sense is for things where you're using, say, advanced geometry that may not be able to be machined, such as complex fluid management parts. So those would be parts with internal channels, parts with veins on the parts to direct fluid in various directions, fluid or air. Complex parts that can't get in, even with 5-axis machining, cannot be manufactured. So that would be a good example of when 3D printing may be used. Bridge production is a great example of when 3D printing or additive manufacturing might be used. Bridge production is going to be the stage between early prototypes and high volume production, where you want to make some parts in the material that is going to either be the same or very close simulation of your production material. Works great because there's no tooling. There's a quick turnaround time, so you can get parts early and fast, and they'll take you through from prototype into, as we say, their bridge production. We mentioned energy absorption here, and that's kind of, say, parts that are going to have latticing. We're seeing a larger uptake of advanced additive manufacturing and 3D printing and additive manufacturing for parts that are for things like shoe soles. You're seeing parts that interface with the human body, goggles. You're seeing helmets that are being made with latticing and lightweighting and energy absorption. So we see down the lower left, there's energy absorption. Up in the upper right is lightweighting. Those kind of can end up being sort of one and the same. Lightweighting is a little different, however, in that you sometimes are going to be taking material out of a part. You're going to want to be latticing. You're going to want to make hollow parts, things where you may not be able to machine them. So your conventional parts maybe were a little heavier. We might end up looking at advanced geometry to lightweight those parts. We'll show an example later. This shows assembly cost and reliability, but part consolidation is a major case for 3D printing, where you say have multiple parts that are machined with or injection molded, or made in some other manufacturing method, conventional manufacturing method, where they have fasteners or adhesive to secure the parts together. And in the case of 3D printing, you can often consolidate those, eliminate the fasteners, eliminate any chance for leaks, and so on. And so you'd end up with a single part, and that can help you reduce your assembly costs and increase the reliability and performance of your part. We were saying that 3D printing, some of the times where it is used very effectively is parts with, as we see on the screen here, high complexity, early in bridge production, material choices, and energy absorption. Let's talk about, and then low or no tooling cost, which is very, very important for 3D printing, and that's a major advantage that it has currently over machining, over conventional manufacturing, such as injection molding. And then customization and multiple disparate parts. We were just speaking about that with part consolidation and producing parts not only together in an assembly cost, but also in a batch. When you're producing an assembly of parts, say a front and back housing and a battery door and buttons and some components that go within that assembly inside of it, but you can often print parts in 3D printing where you are able to print them in one batch, and it makes the part cost very low and the lead time very short. So customization, that can often mean multiple versions of the same part, or a component, an assembly of components where you would print all at one time. So that is a great use for 3D printing. Then we were talking about lightweighting and high complexity, as well as energy absorption, which has a strike through there for some reason. So those are all combined together. Those all can often interchange. So having multiple ways to lightweight, produce high complexity, which in 3D printing, one of the advantages of high complexity is that it often, if anything, decreases the cost because we're using less material. It does not increase machine build time or residence time like it does with machining. So we can produce highly complex parts at really no additional cost or even reduced costs. So let's look at where machining may make sense. Now we'll notice that some of these are not necessarily mutually exclusive from additive. Sometimes it may make sense in, for example, there's no tooling cost often for CNC machining either. So on the right, low to no tooling cost. So really it comes down to machine time. So they can often have very comparable costs. So these aren't necessarily mutually exclusive, which is part of what we'll talk about today as well. So some of the times that it does make sense are when you have very tight tolerances. Additive manufacturing is a wonderful technology with lots of advancements that are making new things possible every day. Some of the technologies, such as DLP and stereolithography, have very tight tolerances. Others, such as SLS and multi-jet fusion, have slightly looser tolerances. Same with FDM, or fused deposition modeling, have slightly looser tolerances. So in those cases, say if you're going to be wanting to produce a part in a production material such as polycarbonate or ABS, but you need tighter tolerances than what can be achieved in additive manufacturing, you're going to want to look at machining. Machining is also excellent for both simple all the way up to very complex geometries. As we mentioned at the early slide, we have 2.5, 3, and 5-axis CNC, and those mean 2.5 and 3-axis mean that you're basically milling from the top in the Z, and the platform moves around in X and Y. 5-axis means that the spindle can rotate at various angles to be able to get into very, very complex geometries. So between 5-axis and then multiple setup, whether it be done manually or done on a gantry, we can achieve extremely complex geometries. And we also are extremely good at producing parts in the split and bond format, where we would machine sections and fabricate them together. So we can get extremely complex geometries, sharp corners, things that can often be difficult to do with 2.5 or 3-axis machining. Machining has a predictable outcome. Machining has been used for several decades. We have materials that are very stable. We have machining centers and programmers that are very consistent. The machine doesn't move. There's not as much thermal variance as there is with 3D printing. So we often end up with a bit more of a predictable and consistent outcome with CNC machining than we do with additive manufacturing or 3D printing. Surface finish is a little more predictable. There aren't often voids that are unexpected and so on that might happen with an FDM part. For example, you may have strong performance from the FDM until a build layer delaminates. Things that are a little tougher to predict with 3D printing are often solved with CNC machining. So we do say that it's a little more predictable. If you have a little bit more time, it might be worth the CNC route. So that's something to consider when you're looking at these projects. Machining and 3D printing or additive manufacturing can both be very fast. CNC machining often takes a little bit more setup. Depending on the quantity, we can go very fast. This can be something to be turned around in 2 to 5 days, significantly under, consistently under 2 weeks. However, if you're producing multiple parts with CNC machining, it tends to need to be done serially. Sometimes you can set them up in a single build and be able to machine out multiple parts, but it doesn't produce multiple parts as quickly as additive manufacturing, of course. So that's one of the reasons that additive manufacturing is being adopted more and more in the marketplace is how do I get more parts through the system faster to be delivered to me? So CNC machining, however, we've got huge capacity. It's generally necessary to have multiple machines to be able to produce very quickly, and we have a huge capacity. That's what machining tends to come down to on lead times is what's your capacity? What type of machines are you running? Do you have high speed spindles? It tends to be much more equipment and operator related than with 3D printing. It's more a matter of which technology and how you're setting up the builds. So CNC is certainly capable of very fast to medium lead times. Quantities I just kind of talked through. We can do typically low to medium quantities with CNC machining. If you get into very high volumes, which we do with CNC, it can be a little less efficient. You don't see a drop off in part price very much, tends to stabilize. So it tends to be used mostly for low to medium quantities. I talked about low to no tooling cost. I want to say low because when you're machining, you're taking a solid block of material and you're milling it away to make the part. You may have some tooling cost up front to either hold the part correctly or post-op to inspect it. So sometimes there is tooling cost in machining, but it is typically not as much. There's not as much of an NRE as there would be, say, with injection mold tooling, where you need to build a tool in order to make your parts. The other case, machining makes great sense in production materials. We produce parts in polymers, we produce parts in elastomers, and we produce parts in metals. Typically in CNC, we're talking mostly the polymers and composites as well as metals. We have a huge range of metals such as brass and copper and aluminum and stainless steel and tool steel. On the plastic side, we're working with ABS and polycarbonate and acrylic. And some of the elastomer materials we can sometimes machine depending on durometer. And then I just briefly mentioned some of the modeling compounds, such as Renboard we use, and even wood. That does come up from time to time. Now, all of those materials are very, very similar in behavior to what's going to end up being a production material or an injection molded material or extrusion or any of the other processes where you're going to be making production parts. CNC has those materials available. They're not often things with photopolymers like they would be with additive manufacturing. Let's talk about what is 3D printing and additive manufacturing with our changeover in the slide presentation there. That's got a little bit out of order. So I just kind of want to go back and talk about just a brief definition of what is 3D printing and what is additive manufacturing. What we're talking about here is, as is shown in the picture, that's a HP Multi-Jet Fusion 5200 machine, our facility in Libertyville. 3D printing, what we're talking about here is an additive process that creates parts, 3D printed layer by layer, laid down either right side up or upside down, depending on the technologies, layer by layer in very thin to slightly thicker layers, depending on which technology, material, setup that you're using. And it lays down the part or adds the material to the bottom layer by layer in the cross section until the part is complete. Additive manufacturing, when we say that term, we just kind of wanted to define here that is usually just 3D printing in quantity. 3D 3D printing tends to imply, these terms are kind of used interchangeably in the market today. 3D printing tends to imply a little bit more prototype, low quantity, quick turn, going to 3D print these parts. Additive manufacturing is typically when you're producing a lot of 3D printed parts to make typically your production parts. That may require some more planning, some more setup, some more inspection plans, and so on. So once we get into those stages, those types of discussion, a little bit more engineering around it, then we're talking about additive manufacturing. CNC machining is, or CNC stands for computer numerical control. It is a subtractive process where you're starting with a solid block or round stock of material, and you're milling the part away using advanced programming and machine tools to form your part. So just clarifying what we mean by CNC machining and 3D printing or additive manufacturing. This slide is set up to talk to some of your questions here. There were a couple of questions that related to volumes and costs, and we wanted to look through that. And a couple of questions on the right are, what are the unit part volume considerations? And then how do the cost structures compare? So this brief little slide shows that typically with CNC machining, and we have cost per unit on the left and units manufactured on the right. So we see a different growth curve than we might see with injection molding or some of the other processes, where we have typically actually a fairly low to sometimes no tooling costs for additive manufacturing or CNC. CNC may be a little bit more because we have more programming. It sometimes can take the intervention of a human to step in and do some programming. We see those costs drop off as we increase volume in CNC till it tends to get a little more flat. Additive manufacturing or 3D, this is what I was just speaking about. There is actually sometimes some upfront cost with additive manufacturing we make versus just 3D printing. We may go through some analysis of a build. We may have some NRE in some engineering, some plans on inspection, and so on. So there often is a small upfront NRE. But from there, you see a reduction in cost, but 3D printing tends to kind of not be an extreme drop off in part cost as units manufactured increase, which is one of the reasons that injection molding is still very relevant. So we see that additive manufacturing can be a big advantage in that tooling cost is typically going to be lower than tooling or injection molding, but the part cost doesn't drop off that much because there's not a massive amount of efficiency gained with multiple parts. You still have to print. The printing, the first build is quite similar to the 10th build, for example. There may be some advantages, so there is some drop off, certainly material cost, but mostly labor and finishing and inspection becomes more efficient as we gain quantity. So some more questions here. We're talking about cost per unit as part complexity increases. And here we see a significant difference between CNC and 3D printing or additive. I mentioned on that earlier hexagonal graphic slides that part cost increases or decreases or isn't really affected, with 3D printing or additive manufacturing as complexity increases. So the questions we have is, how does part size and complexity affect this decision? What about cosmetic requirements? Did you need a separate part drawing? So those actually are separate questions here. But as your part complexity increases, as we see in the lower axis, you see major increase in CNC cost. Whereas with additive manufacturing, if you add complexity, we actually don't increase the part cost substantially. In fact, sometimes it can go down. That's kind of not really shown here, but it certainly can in some cases where you're using less material. But with CNC machining, an additional feature that, say, a side action may create a complete new setup and add significant costs onto the CNC machine part. So part complexity affects CNC machine prices much more than it does 3D printing or additively manufactured parts. We wanted to show an example here of a case where a part actually is more efficient in 3D printing than it was in CNC manufacturing. This is a part that we produced in conjunction with HP. We had an example where we machined the separate components on the left. So they were all machined separately and then needed to be affixed together with fasteners and adhesive. They had some limited performance. We were seeing some performance cases where the parts were not, the material was not flowing through this vent very well. So we worked on consolidating the geometries together to be able to be printed in one continuous assembly. Eliminated fasteners, increased airflow, significant increase in part performance. However, it could still be optimized. So we used finite element analysis and analyzed material flow and fluid flow through this part and realized that we could change the geometry significantly beyond what was kind of traditionally engineered geometry into this optimized, more organic shape, allowing for separation of the airflow through the part, and also more efficient channels from where the air was originating to where it needed to go. And we gained, and it produced a hollow part with very complex geometry that couldn't be machined. And we realized a 22.3% flow improvement for the customer. So not only did it reduce the part cost from the CNC machining example on the left, but it also increased the flow and performance of the part. This is a very good example of how, in this case, additive manufacturing was a better choice than 3D printing, than machining, which is how we had been producing the part previously. So as you all registered, we wanted to talk through the questions that you had. And I want to make sure that we've answered many of them, as many as possible. Some of them we can answer here, and we've gone through and shown. Others are questions that we'll need to follow up and speak with you all directly.
Yeah, so let's get started with one that we've received a number of different questions about, and that's about materials. So would you speak a little bit more into the different options and considerations for materials across the two different technologies?
Yes. So the conversation today is expansive. We're speaking not just about polymer 3D printing or metals 3D printing. We're talking about all of it. Same with machining, elastomers, and as well as rigid materials and metals. So we produce so many different processes and so many different types of materials that putting them all in a graphic is a little complex. But if you go to our website, you can see the materials that we work through. I did kind of go through and mention those materials that we work in with machining, being the traditional metals, traditional plastics that you typically see. We all started to work with composites such as PCABS material. On the metal side, we do work with magnesium. We can work with flame-rated ABS. So there are some materials that we can work with in CNC that we cannot work with as easily in 3D printing or additive manufacturing. So then on the additive side, there's typically the extrusion-based technologies, FFF, fused fabrication, filament fabrication, and then FDM or fused deposition modeling. Those are the Stratasys machines, the 3D printers that were in technical colleges in a lot of OEM company labs. Then there's the powder bed technologies such as multi-jet fusion, selective laser sintering, and then on the metal side, additive metal using the lasers as well as E-beam. And so in those huge range of materials, but those are typically, in those processes, those are typically production grade materials just made in extrusion filament or in powder. And they will perform a lot like your traditional materials. They are just typically compromised by the build layers. So sometimes we want to consider, yes, that is ABS, but it's going to perform a little differently than your injection molded part, depending on part orientation and setup and how we've engineered to run the part. So that's something that we're going to want to look at very closely. So materials are important, what basic material you're producing, but also how you print, how the orientation is. So those are the traditional technologies producing in traditional materials. We also have some of the technologies that are based on laser or DLP, and those are going to be photopolymers, and those are almost all simulations of production materials. So you're looking at acrylic-like and polycarbonate-like and ABS-like, but they're not chemically, they're not the same as the production, the traditional production processes. But they often offer things like clear. They offer high strength. They offer high impact. There's some huge range of capabilities, and we produce parts in just about all of those materials.
Great, thank you, Jesse. Let's see. What about quality? you speak to the quality variances and considerations?
Yes, absolutely. So quality of 3D printing versus CNC. How long will 3D printing items compare to the life of CNC produced? That's a really good question, and it's something that we're all working through, trying to see when 3D printing can, say, replace CNC for some uses to help reduce costs, reduce lead time, maybe make more difficult geometries producible. But you're often limited to because of quality. And by quality, I assume that this person means, say, surface finish or tolerances, build strength or part strength, and a lot of the answer to those questions is often not. It is limited by the technology. You're going to see a smoother surface finish in something like DLP or stereolithography when compared to selective laser sintering or FDM. However, you can change the build orientation. You can work together on how you're going to print the part, where you're going to have supports. If it's a technology such as FDM or stereolithography that has supports that attach the part to the build plate, how you orient the part is going to affect your part quality significantly, probably more than it would with machining in some cases. So there's surface quality, there's tolerances is a major factor. 3D printing can have extremely tight tolerances, again, depending on technology and build orientation, material chosen, sometimes the design of the part. If it's a thicker part and you're producing it in a thermal process, such as HP's multi-jet fusion, you might see some elephant skinning or some bit of sink or cupping that can affect your tolerances. Whereas if you say core the part out, you're going to get a much better performance with tolerance. So it's not necessarily the process. It may be some engineering and how you use the technologies that we can help guide you through that might get you significantly different results out of the same process. And then how long, it's the same question, but it looks like a little different. How long will 3D printing items compare to the life of CNC produced? So what I assume they mean is just life cycle. How many times are they gonna go through, say, a stress cycle? And that's going to depend very much on build orientation, material, design of the part, but they can sometimes perform at least as well as CNC parts. I don't know of a case where it's really like better, unless it's like we talked about with a consolidated part design where it may produce parts that are actually better than CNC. So it just depends on your part design, material, and process chosen.
Great. You mentioned, you touched on finishes a little bit. Can you speak in further depth around the different finishing options and what secondary finishing operations are typically used?
Yes, absolutely. So with machining, typically with machine parts, we're going to use, let's talk about metal. So machine metal parts, you're going to typically use plating for secondary finishing. I should pause and say we can use inserts, we can use helicoils to that kind of secondary. Then for surface finish, we could of course do plating, such as anodizing and Cerakote to provide lubricity to a machine part. There's really a wide range of capability for machined metal parts that includes things like anodizing that you don't do with plastic. We also of course paint, so we can finish parts with painting. On the plastic side, we're not going to anodize, but we can paint. We can Cerakote from time to time on machine parts, but typically, just paint. Or if it's a clear part, we're going to either vapor smooth if it's an acrylic polycarbonate part, or hand polish if it is an acrylic part. And with that, we can get lenses, light pipes, clear parts. And then on the 3D printing side, there are secondary finishing to make parts cosmetic for 3D printing is important. Most 3D printed parts, when they come out of the printer, are going to be things like kind of natural colored, amber, black, sometimes white. If you're printing parts in FDM with pre-colored material filament, you can get parts in color, but typically they're not really cosmetic until you go in and do some hand finishing, where you're going to want to hand finish, primer, and then paint. But we do offer that. There's a huge range of finishes that we can do using paint. We also use, I mentioned Cerakote a couple of times. Cerakote is a ceramic-based paint that's applied to parts at room temperature and then post-baked. to adhere the plastic or the coating onto the part. And that is a fairly newly used technology in mostly multi-jet fusion. We didn't use it prior to multi-jet fusion introduction in about 2017 because the other materials couldn't really take the heat. And so it started being experimented with, and since then we've realized, oh, we can put Cerakote on an FDM part. You can put Cerakote on an SLS part, so it is used a little bit more, and that's exciting. It offers UV stability, it offers lubricity between parts, and of course color.
Great. Looks like the majority of our remaining questions have to do with how both technologies can be best used together to drive efficiencies in production. That's
a good question as well. There's how can you use the parts together? I guess think about this. That tends to mean like, well, can I 3D print a part and then post machine it, or can I do some machining and then 3D print onto it? You can't usually do that very well, but you can take a 3D printed part and mill or machine sections of it to get things like smooth surfaces on an additively produced part in metal. You can do the same thing in plastic as well. So if you have a bearing surface, or if you need a datum, you need a flat sealing surface, using a combination of 3D printing to say get very high complex part, and then machining to get a flat surface or sealing surface is a great way to go. We do offer both of those technologies, and we can combine them to get the best objective. So there's that. There's also a time where you may machine assemblies that you may machine portions of it and 3D print portions, where in the past you maybe had done it all in machining. And so you may be able to affix parts together with a 3D printed section that is in one material, and then a machined part that's in another disparate material. So that often happens in programs that we work on. And then, as Brian has shown here on the slide, these technologies can often be complementary, where the two technologies are adopted alongside of each other, and the benefits are greater than if they were adopted individually. Something else to consider is not just I have to decide whether I use additive manufacturing, 3D printing, or CNC. You may start with a 3D printed part. Maybe something that is, as I mentioned earlier, you may have a series of parts that you need to produce, and 3D printing them early to get you your form factor, kind of check out, make sure things fit in general, that they look good, that your stakeholders that care about the appearance and so on are happy before you step into machining as the next stage. They may be complex parts. They may require some setup that is a little bit more costly than it would be of 3D printing. So try 3D printing them first, prove it out, make sure it's good, and then step into machining. And then your next steps may be injection molding beyond that. So it's part of the continuum is the process here, where they may be used together. So it's not just, can I use it individually on that part, but can I also use them in series to help me achieve my objectives with my product development program? Let's wrap up. If there aren't any additional questions, we wanted to show some contact information for me. Again, I'm Jesse Lee at Uptiv, always available to help with any specific questions that you have or problems. There's discussion that we have that is no obligation, of course. You can just call and speak with us, send CAD files. We can take a look and walk you through the possible options. I work primarily on the West Coast and with our team in advanced injection molding. The rest of our team does a lot of advanced 3D printing, and you may submit your RFQs to the Uptiv manufacturing website or at the email of hello@uptivmfg.com. We invite any inquiries to come in our way. If you have any questions, please follow up. We'll be in touch, and we thank you very much for your time today.